Hi everyone, my name is John Parker, and for part C of our project on Joule's first law, I'll start by explaining the original process that led to this important discovery. Before Joule's time in 1978, Count Rumford was working in a military workshop in Munich, Bavaria. He was supervising the manufacturing of cannons and noticed that a lot of heat was being produced while boring out the metal barrels. This wasn't a formal laboratory experiment, it was actually a practical observation that took place in an industrial setting. Rumford used a large brass cannon, a steel boring rod powered by horses, and a container of water surrounding the cannon. He placed a thermometer in the water to measure how the temperature changed during the boring process. As the boring tool rotated inside the cannon, friction generated a continuous amount of heat. Rumford noticed that the water around the cannon kept getting hotter and hotter, even after a long time, which suggested that the heat could be produced indefinitely from motion. At the time, Rumford didn't have modern measuring tools, so he couldn't precisely calculate how much heat was produced. Still, he was motivated by curiosity. He wanted to understand whether heat was really a material substance known then as caloric or something else. His results showed that heat came from motion, not from a mysterious fluid. This challenged the accepted caloric theory and opened the door for later scientists, especially James Prescott Joule, to study heat as a form of energy. Now let's fast forward to how this process has evolved in modern science. Today, scientists use electrical circuits to study Joule's law. Instead of friction, we generate heat by passing an electric current through a resistor. We measure the current and voltage with digital meters and record temperature changes using sensors connected to computers. This allows for very accurate calculations of the heat produced following the operation. The equation Q is equal to I squared or T. Compared to Rumford's rough setup, the modern method is much more controlled and precise. We can isolate variables, use clean electrical energy instead of mechanical work, and conform the relationship between current, resistance, and heat with very high accuracy. Joule's law is used everywhere today, from electric heaters and furnaces to cord frosters and industrial systems. It's also essential in designing energy-efficient devices and keeping electrical circuits safe from overheating. Looking ahead, researchers are exploring new materials that can control or reduce heat loss and ways to use Joule's heating in advanced fields like nanotechnology and medical therapy. These developments continue to build on the same principles first observed over 2 centuries ago. Count Rumford's accidental discovery and Joule's careful experiments helped transform our understanding of heat, energy, and motion. Together they laid the foundation for the first law of thermodynamics, an idea that still powers science and technology today. That's it. Thanks.
Hello everyone, my name is Adrian Miranda and these are my partners John Parker and Sebastian Crangeras. Today we are on part C of Joule's first law. The original process is that James Prescott Joule first tested his law on electrical heating in the 1840s. He used a copper wire coil immersed in water and connected it to a battery. When current passed through the wire, it heated the water. Joule measured the rise in water temperature, the current, the resistance, and the time to calculate the amount of energy produced. This led to the relationship known as Joule's first law, H equals I squared R2, or I2R2, where H is the heat energy, I is the current, R is the resistance, and T is time. Now I'm going to be talking about the original difficulties. At the time, Joules had limited tools. He had no digital instruments. He had to use manual thermometers and stopwatches, which introduced human errors. He was also measuring current and resistance, which was difficult because early batteries provided unstable voltage. The theory of energy conservation was not yet accepted, so many scientists doubted his results. Controlling heat loss to the surroundings was nearly impossible in the 19th century equipment, and here you can see all the digital stuff he could have had but doesn't. His original motivation was that he wanted to prove that the heat was a form of energy, not a mysterious caloric fluid, as people believed then. He aimed to show that mechanical, electrical, and heat energy were all related and could be converted from one form to another. This motivation helped lay the foundation for the law of conservation of energy. The original benefits is that when he first discovered joules, work helped disprove the caloric theory. It also provided one of the first experimental links between electricity and heat. His findings also helped establish the first law of thermodynamics. Engineers began applying this to early electric heating devices, motors, and electrical safety systems. The modern process of today is that Joule's law's experiment is performed using precision digital ammeters and voltmeters from accurate current and voltage readings. Calorimeters with temperature sensors and computer data logging for real-time analysis, stable DC power supplies instead of unstable batteries, and in industrial labs, simulation software models the heating effect before experiments are run physically. The experiment can even be done virtually in physics simulations that perfectly account for heat loss and resistance. Modern differences were that modern tools eliminate measurement errors Joule faced. Also, heat losses can now be mathematically corrected or minimized using insulation. Digital automation records thousands of data points per second. Joule's law is now integrated into circuit design, software, and thermal analysis programs for engineering. Modern benefits are now electrical engineering, which predict heat loss in wires and circuits, electronics that now prevent overheating in devices and batteries, HVAC systems, which design electric heaters and resistant coils, energy efficiency, which improves insulation and reduces wasting energy. It also supports renewable technologies such as solar heating and electric vehicles where heat management is essential. The future expectations are that nanomaterials with lower electrical resistance to reduce unwanted heating, and for superconductors that can carry current with almost no energy loss. They also want AI-based thermal management systems that optimize power use, and sustainable energy applications improving heat recovery and efficiency in modern grids. And that is it for our Part C.